Hello and welcome back to JEE Chemistry Tutor. Before going forward towards our next topic of discussion, let us go back. Now those who have been following the Stereochemistry course and especially our channel, you should remember in the part 1 of our playlist we introduced configuration and conformational isomerism. And what did we talk about conformational isomerism? What are conformational isomers? Conformational isomers are those which can be converted to one another by simple rotation around a single bond. In that case, the rotation is free. And then we talked about restricted rotation and how it is possible in order to generate geometrical isomers. So this is a little rewind, and before going forward, I told you in that conformational isomers example that this is an example of Sawhorse projection. And I told we will come back to Sawhorse projections later. Now, as you can see that conformational isomers are what? They can be converted by simple rotation around a single bond. So there may be many isomers. So in order to properly depict these isomers, scientists came up with different projections in order to classify these isomers. So the different projections are as given. They are wedge dash projection, Sawhorse projection, Newmann projection and Fischer projection. The consequent examples are given here. This is the wedge dash projection. I'll write in short. WD is for wedge dash. This is Sawhorse. This is Newmann. And this is Fischer projection. So these are different examples of projections. What does projections do? These are conformational projections. So these projections are used to depict the different conformational isomers. This can have many conformational isomers, as I told before. This also can have many conformational isomers. So we'll talk by one what are these projections. Now how important are these projections? And then we will move forward to how to interconvert between these projections. And that is very important from an exam point of view, because in exams these questions come where you have to interconvert from Sawhorse to Fischer, suppose from Newmann to Sawhorse or Newmann to Fischer, and interconvert between these projections. But before going to the interconversion, let us learn what are these projections. First we will go to wedge dash projection. I will not talk much about this wedge dash because again, if you remember, this is a little recap. In the part 1 of our Stereochemistry playlist, we talk about these bonds. These bonds, remember, this is the wedge bond, this is the dash bond. What does it depict? They depict above the plane and below the plane respectively. And also let us first remember that these conformational isomers are only possible when the rotation is free. In which case the rotation is free? When we have a sigma bond. Now the question arises, when do we have a sigma bond? We have a sigma bond when we have a sp3 center in an acyclic system. Why a cyclic system? Because as soon as we go to a cyclic system, even if we have a single bond, it consists of both sigma and the pi bond of the ring. And in double bond and triple bond in acyclic systems, there is already a pi bond. So simple free rotation is allowed only when we have a single bond or only when we have a sigma bond. When do we have a sigma bond or when do we have a single bond? When the carbon is sp3. Now from your knowledge of sp3, you should know that when carbon is sp3, its structure is essentially tetrahedral. What is a tetrahedral structure? The tetrahedral structure is like this, where two substituents are in the plane of the system and one substituent is above the plane of the system and another substituent is below the plane of the system. That is, two substituents are in the plane and two substituents are out of the plane of the system, whether above the plane or below the plane. Suppose methane, here two hydrogens are in the plane and one hydrogen is above the plane and one hydrogen is below the plane. That is, two hydrogens are in the plane of the system and two hydrogens are out of the plane of the system. Whenever carbon has a sp3 structure or whenever free rotation is allowed in order to generate conformational isomers, it should always have a sp3 hybridization. Remember this. Conformational isomers is only allowed when we have a sp3 hybridization. And so whatever projections we will learn from here will only occur for sp3 hybridization. In such cases, conformational projections will arise where two of the substituents will be in the plane and two substituents will be out of the plane. Either above the plane, one is above the plane and one is below the plane. This is how we represent conformational isomers. So wedge dash projection is used like this. This is an example of a wedge dash projection. See, any of the carbons you can choose. We choose this carbon, suppose. See, this methyl is in the plane. This carbon is also in the plane. This methyl is above the plane, that is out of the plane. This hydrogen is below the plane, that is out of the plane. So two of the substituents are in the plane and two of the substituents are out of the plane. Okay. This is simply a wedge dash projection. Okay. Let us get to the second kind of projection, which is a Sawhorse projection. A Sawhorse projection is often depicted as a Y projection. Why it is Y? Suppose I draw this. I will come to what is eclipse projection and what is staggered projection. How can I draw this? Suppose I draw a straight line and I put methyl here, hydrogen here, chlorine here, this one, this carbon I put it here, and again here methyl, fluorine, H. I draw the substituents methyl, hydrogen, chlorine, methyl, fluorine, hydrogen. Is there any difference between these two? They're the same, right? I just drew them from there to there. I just made a straightforward view. This is more of a sidewise. This is a sidewards view. This is more of a straight view. See, this resembles two Y's pointing downwards. Or it can be represented like this, where the Y's are pointing upwards. See why it is called a Y projection, because both the carbon centers with respect to which we are drawing the conformational isomers, they are in the shape of a Y. So that is why a Sawhorse projection is often called as a Y projection. Whenever you see a projection which has a Y shape like this or like this or like this, it is always told as a Sawhorse projection. See, this is a Sawhorse projection, two Y's, one Y, this is another Y. Why we call it as an eclipse projection? When both the Y's are either pointing downwards or both the Y's are pointing upwards, means they are pointing in the same direction. Then that projection is called an eclipse projection. Then what is a staggered projection? See this. I'll draw this in this sense, like straight view sense. So in this case, one of the Y's is in this shape. Here is the methyl, hydrogen, chlorine, and another Y is pointing downwards. See, one of the Y is pointing upwards like this. This is like this kind of a system. One of the Y is pointing upwards and another Y is pointing downwards. One's head is correspondence in the same line to one's tail. That means it is a staggered projection. That is, the Y's are pointing in different directions. So students, when the Y's are pointing in the same directions, whether both up or both down, it is an eclipse projection. And when the Y's are pointing in different directions, it is a staggered projection. Now, one thing before I go further forward is all conformational projections, all. Like I'll talk about Sawhorse here, I'll talk about Newmann here after this, which is very important. And then we'll talk about Fischer. We can interconvert the atoms. Now, what do I mean by that? I can keep the whole of the system fixed, like I can keep this part fixed. And I can interchange all the three substituents of one of my substituted carbon atoms. That means I can change one of the substituted carbon atoms because in here the rotation is free. As the rotation is free, we can change the substituents without. So in all these projections, always remember that we can keep one part of the fixed and we can change only one of the carbon atoms. That is, the substituents of only one of the carbon atoms, keeping the other part of the molecule fully fixed. And this is applicable in all the projections we will talk about here, in all conformational projections. Why is this applicable? This is applicable because the rotation is free. Had the rotation been restricted, this wouldn't have been possible. But since the rotation is free, scientists came up that if you want to change from one conformational projection to another conformational projection, you can keep the whole of the molecule fixed. And you can change and you can rotate one of the carbon atoms, the substituents around one of the carbon atoms, so as they can change positions. This leads us to a very important question. How can we then change a staggered projection to an eclipse projection in Sawhorse? I'll draw this again. Suppose I want to change this projection. So this is a staggered projection first of all. I have to change it to an eclipse projection. That is, both the Y should be either pointing up or both the Y should be either pointing down. That's my aim. So I keep the whole of the molecule fixed, but I change substituents on this carbon atom. Another trick I'll say is another uniformity. This is not a trick mostly, that whenever you change the projections, try to change it always you change it in one direction, but try to change it in the clockwise direction. I have always benefited from changing it in the clockwise direction. Whatever you rotate, always rotate in the clockwise direction. Obviously, all three atoms have to be rotated in the same direction. You can't say I will rotate hydrogen in this direction and methyl in this direction. That is not possible. All the atoms have to be changed. Like, suppose if three of the atoms are pointing here, like here and here, They all have to change like this, like so that the whole system changes like this. You can't change one of the atoms like this and expect that this will go like that. That is not possible. That is not feasible. The bond will break then. So all of the atoms have to change. This is like a scientific point of view. All of the atoms have to rotate in the same direction. So suppose I rotate this towards the clockwise direction. So what will happen? What will be the projection? This hydrogen will come here, this chlorine will come here, this methyl will come here. So if I rotate this molecule, what will be the projection I'll have? I'll draw the straight line. This is a way of drawing a Sawhorse projection. First draw the straight line, okay, which depicts the central atoms. Then you draw one of it, which I have kept fixed. So I will keep it fixed here as well. And then I'll draw this. See, hydrogen comes here by rotation. So this is a hydrogen. And we have, see, chlorine comes to this position. It was here, it by rotation, clockwise direction, it came here. Methyl, which was here, goes to this side. This is an eclipse projection. So how can we change from a staggered to eclipse, or in the same case from an eclipse to staggered? By keeping whole of the molecule fixed and by rotating the substituents around one of the carbon atoms or around one of the vertex. That is allowed because the rotation is not restricted. It is a free rotation. So this is how you move from an eclipse configuration to a staggered configuration in a Sawhorse projection. Again, Sawhorse is also known as Y projection. How do we convert this to a wedge dash or a Fischer projection? We'll come to it in the next video. But let us look at what is our next projection. Our next projection is a Newmann projection, which is also known as a side view projection. Why is it known as a side view projection? This is our molecule. This is the same as this. So when we draw a Newmann projection, we keep our eyelids fixed here. That is at the sides. We keep our eyelids on the sides and we look through this side. Okay, we look from here. So in order to draw a Newmann projection from a Sawhorse projection, we keep our eyes at the sides of the Sawhorse projection. And we try to draw the Newmann projection from there. So what will we see if we see from this side? So we'll see hydrogen in this side, chlorine on this side, and the methyl is here. This is like the Y projection of Sawhorse. So we just drew it. Now from this side, this atom or this vertex we will not be able to see, or it will come at the back side of the molecule. So if we are seeing straight from here, and if suppose this is X and this is Y, we will be seeing X clearly, but the Y will be like blurred from us. So how do we draw Y? We draw the Y in the backward direction. So we can't draw Y here, so we draw a circle here. A circle enclosing this, and we see the Y is in outside the circle. That is, it is blurred, or it is in the back side. So from whichever side we are seeing, this is the front side, this is the back side. Same case, this is the front side in a Newmann projection, which is projecting into the circle, and the one which is projecting from outside the circle, this is the back side, or one of the vertex which we can't see, or which is far away from us. So this is how we convert a Sawhorse projection to a Newmann projection. Again, I'll give a brief overview. We keep the eye at the sides. It is a side view projection. Newmann projection is also known as a side view projection. We keep our eye at the sides so that the first vertex appears the closest to us. We draw this first vertex as it is in the shape of a Y. The other vertex or the far away vertex lies away from us. So we draw it away from the molecule, or away from outside the circle. Again, one which is close to us is inside the circle. One which is away from us is outside the circle. I hope you have got it. This is very easy. So if you have got it, please pause the video here and try to the Newmann projection of this molecule. I'll draw it. So if you understood, draw it in your way, and then you see whether what you have drawn is same as what I give here. Another question that arises is like, what if I keep the eye here? Yes, you have all the rights to keep the eye on that side. Then that if you keep the eye here, this star center will be your front center and the other center will be your back center. So you can keep the eye in any way possible. That is up to your discretion, but you should always remember the place where you are keeping the eye, that should be your front carbon, and the carbon atom which is far away from it should be the back carbon. You should not confuse in that case. Okay, let us do the Newmann projection. For simplicity sense, I keep the eye here. Methyl, hydrogen, chlorine. Methyl. Okay, this is a staggered configuration. We know from Sawhorse projection. This is the eclipse configuration. Again, we know from Sawhorse projection. We'll come to what is staggered and eclipsed here. Okay, front carbon, we put it forward. We draw a circle. This is how you draw a Newmann projection. The front carbon first you draw it, then you draw a circle, then you draw the outside ones. Okay, what, like suppose I put it here, here, here. Another thing you must remember, see, I put the carbon on the left side of this. So all of the atoms should be on left side of that one. Should maintain uniformity. You shouldn't draw this on the left side. This bond should be here and this bond is here. So you should not be haphazard. If you draw it on the left side, all of the atoms should be on the left side. If you draw it on the right side, all of the atoms should be on the right side. Okay. Let us draw. This is also a Y, which is the back carbon. So methyl. Here it is a fluorine. This is H. Right? This is the Newmann projection of a eclipsed configuration, and this is the Newmann projection of a staggered configuration of Sawhorse. Okay, so you understood how to convert a Sawhorse projection to a Newmann projection. Very easy. So this is something that will also come in handy in our next video when we interconvert projections. So I will not explain it there again. So since I've explained it here, so do not forget this, and whenever you come to our next video, just use this knowledge there. Again, how do we convert from a Sawhorse to Newmann? We keep the eye on one of the sides. As I said, it's a side view projection. We keep the eye on one of the sides. The vertex closest to us is the front carbon or the front vertex. We draw it out inside the circle. The vertex far away from us is the back carbon or the back vertex. We draw it outside the circle. How do we draw it? We first draw the carbon atom front of us in simple Y, whatever way it is given. See, it was given in this Y, that is Y pointing upwards, so I drew it like this. Here the Y was pointing downwards, so I drew it like this. So whatever way it is given, you just draw it like that. Don't try to change the projection, it will become difficult. So whatever way it is given, just draw it like that, and then just go to the back carbon and draw it again in whatever way it is given. Then it will become easier. Okay. Newmann projection doesn't end here. Newmann projection is a very important role. Now if you see the angle around this point, and since this is a circle, you will know from your maths understanding that the angle around this point is 360 degree. That we can rotate it around 360 degree. So we thought of rotating it around 60 degree so as to generate different configurations. Now here you may not always understand the difference in configurations. You may say, okay, so this and this configuration, okay, this and this configuration are the same. But in cases where the substituents are different, here the substituents are same. But in cases the substituents are different, the projections become different. That is why there are always 6 projections of a Newmann configuration. Which is more stable, we'll come to it. First, let us see what is this. Why this is called the anti-configuration? Because the same size substituents are the same substituents. While I say size, it may happen that this is bromine, the others are hydrogen. They are comparable size, or they are more in size than hydrogen. So the same size of the substituents also matter. Not only the same substituent. Not always substituents will be the same. You have to understand the group of substituents or the size of the substituents. So same size substituents are 180 degree with respect to each other. When the same size substituents are at an angle of 180 degree with respect to each other, that conformation is called an anti-conformation. If we change the angle of this by 60 degree, suppose I rotate this by 60 degree. This methyl goes here, this methyl goes here, this hydrogen comes here, this hydrogen comes here, and we get this configuration. So all are rotated by 60 degree. This is called a fully eclipsed conformation. This methyl and hydrogen are close by each other. This is also close by, this is also close by. See one thing, if I drew this on the left, this is also on the left, this is also on the left. So I should maintain this uniformity always. Okay, so this is a fully eclipsed conformation. Again I rotate it by 60 degree. Suppose I again rotate it by 60 degree. And I'm only rotating the back carbon. As I said, when we change the projections, we only rotate with respect to one of the vertex. The whole of the molecule remains the same. Only with respect to one of the vertex, we are changing it. That is allowed in all projections, as I said before. So I'm only rotating the back carbon atom. So this methyl comes here, 60 degree. This hydrogen goes here. This hydrogen comes here. And what we get is a gauche conformation. Why Gauche? See this methyl and methyl, again I will talk about same size, not always they will be same substituents. Here you are seeing methyl methyl, it may be methyl bromine also, it may be methyl hydroxy, it may be methyl amine NH2 group also. So similar substituents are at an angle of 60 degree. This angle is 60 degree with respect to each other. When similar size substituents are at an angle of 60 degree, it is called a Gauche conformation. When similar size substituents are at an angle of 180 degree, it is called an anti-conformation. And when similar size angles are at an angle of 0 degree, this may not seem so much similar, but this is 0 degree. Just so that you can understand, I have drawn it far apart. But these are on top, or these are like, this is front, this is back. It is at an angle, these are parallel to each other. So this is at an angle of 0 degree. So when similar size substituents are at an angle of 0 degree, it is called a fully eclipsed conformation. So you got what is an anti-conformation, fully eclipsed conformation, and a Gauche conformation. Rest of it is the same. Again, we rotate it by 60 degree. It comes to this one. This is a number 4 system. This is also a fully eclipsed conformation, same as this. Again, the angle is 0 degree, so it's a fully eclipsed conformation. We again rotate by 60 degree. This methyl comes here. This hydrogen comes here. This hydrogen comes here. We get again a Gauche conformation with the similar size substituents again at an angle of 60 degree. Now we again rotate by suppose 60 degree. Again the methyl comes here, the hydrogen goes here, this hydrogen comes here, and what we get is again a fully eclipsed conformation. You can say again it is rotated by 60 degree. If we rotate by 60 degree, this methyl comes here, this hydrogen goes here, this hydrogen goes here, which is same as this number 1. See, this methyl is here, this hydrogen is here, this hydrogen is here. So if we rotate this by 60 degree, we will get back to number 1. So in Newmann projection, we always rotate by 60 degree and we will have only 6 projections. We can't have more than that. You can't create a probability of projections. There will always be 60 degree rotation and there will be 6 projections. Of them, 2 of them may be Gauche, 1 is anti, 3 fully eclipsed. It depends on substituents we have. So you understood what is Gauche conformation and what is fully eclipsed and what is anti. When similar size substituents are at an angle of 180 degree, it is anti. 60 degree, it is Gauche. 0 degree, it is fully eclipsed. So if given a conformation, you can understand whether it is a Gauche conformation or an anti-conformation or fully eclipsed conformation. Okay, let us see whether you have understood. Tell me whether this configuration is a fully eclipsed configuration or a Gauche conformation or anti-conformation. Look at the molecule carefully. So what is it? It is an anti-conformation. Why is it an anti-conformation? See, methyl, methyl. When you have the same substituent, you don't have to look at anything else. When you don't have the same substituent, then you look at similar size substituents. But when there is 2 methyls, you don't have to look at anything else. These 2 methyls are at an angle of 180 degree. And what did I say? When similar size substituents are at an angle of 180 degree, it is an anti-conformation. So this is an anti-conformation. This is a fully eclipsed conformation. Why? Because the methyls are at an angle of 0 degree. See, this methyl and this methyl, they are at an angle of 0 degree. When 180 degree, remember this and always remember this in Newmann projection. When similar size substituents are at an angle of 180 degree, it is an anti-conformation. When similar size substituents are at an angle of 0 degree, it is a fully eclipsed conformation. 60 degree, it is a Gauche conformation. What conformation is there depends on similar size substituents and its angle. When we have the same substituent, you don't have to think about similar size substituents. Same substituent, just compare the same substituents. If you don't have the same substituent, then the similar size substituents comes into play. Okay, now you may ask that, okay, we can change from one conformation to another conformation by just rotating by 60 degree, and it is allowed since it is a conformational isomers and rotation is not restricted, the rotation is free. So we can change the conformation. Then how will you say that which conformation is more stable? So let us draw a molecule, suppose this one. This is an anti-conformation. Now in this case, I will say that this is more stable than the Gauche conformation. And when we are thinking about stability, mostly the stability lies between anti and Gauche. The fully eclipsed conformation lies in between anti and Gauss. Like if I say the anti conformation is stable and the Gauss conformation is the most unstable, then the fully eclipsed conformation lies between the anti and the Gauss conformation. And this is always true. Whatever conformation you see, you will always see in the anti and the Gauss conformation. The fully eclipsed conformation is like the middleman. So whenever you are asked to pick which Newmann conformation is more stable, it will always lie between anti and Gauss conformation. It's like a true or false. Okay, anti or Gauss conformation. Fully eclipsed conformation is like in between the anti and Gauss conformation. Okay, so if I draw the Gauss conformation of this, the same molecule. What is a Gauss conformation? When same substituents are at an angle of 60 degree. Here it is an angle of 60 degree. Here it is an angle of 180 degree. So when it is an angle of 60 degree, there will be considerable steric bias of one on the other. This both methyl are bulky substituents compared to hydrogen. So this methyl interaction will be much more, or its energy will be much more in case of Gauss conformation. That is, methyl interaction is much more in Gauss conformation. If you see in anti-conformation, there will be a methyl hydrogen interaction. So if you are comparing, here we have a methyl interaction, and a methyl hydrogen interaction. One methyl and one methyl hydrogen interaction. But in this case, we have two methyl hydrogen interactions. That is, two methyl hydrogen interactions. Since methyl is bulky, much more bulky than hydrogen, and this rule applies to all substituents. Since all substituents are more bulky than hydrogen. If you consider bromine, chlorine, fluorine, they all are more bulkier than hydrogen. So that interaction will be much more destabilizing. Since there is a methyl interaction, it will be much more destabilizing than methyl hydrogen interaction. So whenever you have a bulky substituent, they will always lie in anti-conformation. Whenever you have two bulky substituents, they will always lie in anti-conformation, or anti-conformation will be the lowest in energy whenever you have bulky substituents. Then you may ask me, okay, then Gauss conformation is never stable? Always anti-conformation is stable? No, Gauss conformation is stable, and its stability arises from hydrogen bonding. Let us see how. Suppose in place of methyl, I just replace it by OH group, and let us draw the anti and the Gauss conformation. So this is the anti conformation where the two hydroxy are at 180 degree with respect to each other. This is the Gauss conformation where the two hydroxy. This is the Gauss conformation where the two hydroxy are at an angle of 60 degree with respect to each other. Why till I say that when there is a hydroxy, the Gauss conformation is more stable? Here the Gauss conformation is more stable due to hydrogen bonding. See, this hydrogen bonding exists only when it is at a Gauss conformation. This hydrogen bonding exists. So Gauss conformation, now this hydrogen bonding does not exist when it is an angle of 180 degree, right? It is an anti-conformation. The hydrogen bonding exists only when it is in a Gauss conformation, and that is why Gauss conformation is stable only when there is hydrogen bonding. So remember students, only when there is hydrogen bonding, then only Gauss conformation is stable. In all other cases, the anti-conformation is stable. What is hydrogen bonding, or which groups show hydrogen bonding? Highly electronegative groups like oxygen, nitrogen, fluorine, and in some cases chlorine. These are the only groups which show hydrogen bonding. No other groups show hydrogen bonding. In this case, it was an interaction between two methyls, so no hydrogen bonding is possible. Suppose if one of the methyls, I replace it by an OH group. Suppose I put a OH group here. Then also hydrogen bonding is not possible because one of the substituent is a methyl whose electronegativity is much less. So hydrogen bonding is only possible when it has high electronegativity. When we have a OH group, NH2 group, or a fluorine groups. These are the three, chlorine in some cases but not much. These are the three groups which only show hydrogen bonding. And whenever you have a Newmann projection having two of these groups, like two of the substituents are by these groups, then only we will have a Gauss conformation. If one of the substituent is of these groups, suppose one of the substituent is OH and another substituent is CH3 as I explained here, then hydrogen bonding will not be possible. In such cases, anti-conformation will be possible, or anti-conformation will be more stable. Why? Because of steric hindrance. because steric hindrance will be less when there is an anti-configuration. But whenever hydrogen bonding is possible, the hydrogen bonding energy compensates the steric hindrance and makes the Gauss conformation more stable. So if you are given a Newmann projection and asked to depict stability, you first look at hydrogen bonding, or you first look whether there is an OH group, NH2 group, or a fluorine group. Remember this table. These groups only show hydrogen bonding. And if in the Newmann projection, two of the substituents are from these groups, there is a OH-OH, or suppose a OH fluorine, or a NH2 fluorine, or suppose OH NH2, two substituents are there, then only Gauss conformation is stable. If no such two substituents are there which can show hydrogen bonding, then anti-conformation is stable. So from here on you can depict which conformation is more stable. So questions may arise where the examiner will give you a Newmann projection and tell you, or they may give you any molecule and ask you to draw the most stable Newmann projection. So you should understand which is the most stable Newmann projection. How do you understand? First look whether you can exhibit hydrogen bonding. How will you exhibit hydrogen bonding? If there is an OH, NH2 or fluorine groups are there. Two such groups must be there. Remember, two such groups. One will not suffice. Two such groups must be there. If two such groups are there, then hydrogen bonding is possible. It is a Gauss conformation. If two such groups are not there, hydrogen bonding is not possible. Anti-conformation is the most stable. Before wrapping up Newmann projection, another question that arises is when you have a fully eclipsed conformation. That is a fully eclipsed conformation, suppose of the same molecule. So many questions arises from students that, sir, in this conformation also hydrogen bonding is possible. Absolutely right. This conformation also can show hydrogen bonding. But in this case, the steric hindrance of these close by atoms, because they are at an angle of 0 degree, it is so large, the steric hindrance is so large that it compensates or it overcompensates the hydrogen bonding energy. That is, in a fully eclipsed conformation, the steric energy is more than the hydrogen bonding energy. And so the molecule tries to release this steric hindrance, or it tries to release this crowd. As in order to release a crowd, it goes to the Gauss conformation, which then becomes the most stable. So that is why Gauss conformation is more stable than fully eclipsed conformation, even though fully eclipsed conformation can also show hydrogen bonding. But in Gauss conformation, due to the combined influence of lower steric hindrance and more energy from hydrogen bonding, it is more stable than fully eclipsed conformation, which is very high steric hindrance, even though the hydrogen bonding amount is the same. So again I say only two conformations may be stable, either the Gauss or anti. Fully eclipsed always lies in between. How do you depict? You see hydrogen bonding. If there is hydrogen bonding possible, Gauss conformation. If not, anti-conformation. It's very simple. You only look for hydrogen bonding. So I hope if you are asked any question about which projection is most stable in Newmann projection, I hope you can do it. Okay, we'll come across questions later. Let us look at the last step of it. We'll learn a Fischer projection. These are the simple examples of Fischer projection. This is a sugar molecule. And if you have come across many sugar and carbohydrate molecules, you will see that they are represented in Fischer projection. It is much more easier to represent them in Fischer projection. How do we convert from wedge dash to Fischer? Because that is very important. That is the most important thing for an exam point of view. If you are given a molecule in wedge dash, you have to convert it into the Fischer projection. How do you convert it? We'll come to it in our next video. So don't miss out in our next video. Do look for it. But right now, what I will tell about Fischer projection. Now, many books will say that, okay, this is above the plane, this is below the plane. Now, the vertical line is above the plane, the horizontal line is below the plane. I will not go into the intricate details because it makes you confused. I'll just say, look at, there are two lines. There is a vertical straight line, there is a horizontal straight line. This is a Fischer projection. In a Fischer projection, this vertical line means the molecule is in the plane. Whichever substituent is in the plane is depicted in the vertical line. And the horizontal line shows the substituents which are out of the plane. Whenever the substituents are above the plane or below the plane, that is out of the plane, they are depicted by horizontal lines. That means in this case, this CHO, this carbon intersection, this carbon intersection, this carbon intersection, and the CH2OH are all in the plane. That is, they are in the plane of the system. And this hydrogen OH, OH, hydrogen, hydrogen OH, which are all on the horizontal line, they are out of the plane. They are either above the plane or below the plane. If you look at here, this methyl, this carbon intersection, this carbon intersection, this methyl are in the plane of the system. this hydrogen, fluorine, this chlorine and this hydrogen, they are out of the plane of the system, either above the plane or below the plane. This is what you only have to know about Fischer projection. There is not much complexity in Fischer projection as there is in maybe Newmann projection or Sawhorse projection. But Fischer projection is very important when you interconvert projections. When we change from a wedge dash to Fischer, Sawhorse to Fischer, these are very common examples or very common questions for examiners where you need to convert the projections. So this is all about Fischer projection. So today we learned about all types of projections. Wedge dash, we learned about Sawhorse, we learned about Newman, and then we learned about Fischer projection. We also learned which Newman projection is most stable. It's very important from exam point of view. You need to understand which Newman projection is most stable, and you understood how to depict stability in Newman projection, whether anti-conformation is most stable or whether Gauss conformation is most stable. Also, we did a little prelude where we learned how to convert a Sawhorse projection to a Newman projection. It will come in handy in our next video, and it will come in handy in interconversion of projections. So today we'll end it here. So we have some questions we would love you to solve. This is which Newman projection will be most stable, that is either anti or Gauss. So you have to tell which Newman projection is most stable out of these 5 examples. A footnote: in the first example there are 2 things. They are at low pH and high pH. Both are different. So think about it. It's a very good question. It's a very intricate question. Think about it. Apply your instincts. What happens at low pH? What happens at high pH? See at what pH hydrogen bonding is possible. I give a very big hint. It may be possible hydrogen bonding is possible at both the pHs. So think about it, which case hydrogen bonding is possible. Before ending it, I'll say this number 5. This number 5, you have to draw the most stable Newman projection. You can't just say anti and Gauss. If you draw the Newman projections, you will understand that there are more than one anti and Gauss. So in number 5, you have to you have to draw the most stable projection. In all of the cases 1, 2, 3, 4, you have to just tell whether Gauss or anti is most stable or not. But in number 5, you have to give me the drawing of the most stable Newman projection. We'll end this video here. Next video we'll start how to interconvert projections. But before that, please do this, solve yourself so that you have a clear idea of Newman, Sawhorse, Fischer and wedge dash projections. These are all the projections that come in for exam point of view. There are no other conformation projections, and I hope you have understood all these projections. If you like us, do share, subscribe, and do not forget to ring the bell icon for further updates. And we'll see you in the part 6 of our Stereochemistry course.